Fellow says, please make a video on current Nobel Prize winner. He should have put an S there, winners, because as always, lately they've been giving all these prizes to lots of people. Usually three. Okay, and so the question is whether anyone alone is ever going to get a Nobel again. Now it's always divided into three. They get a penny each and a bottle of champagne, I guess. Yeah, these people, they won the Nobel Prize this year, okay, in physics, supposedly physics, mathematics. That's what they won it in, and here they are. Let me present them, okay? Okay, these are the Nobel Prize winners this year. And what did they invent? What did they come up with? And you would have to go back almost to the 1980s to figure out what these people proposed or what they found out. And it's got to do with something called entanglement. Okay, what is entanglement? People say, I never heard of that. Maybe. Some people have heard of EPR, Einstein, Podolsky, Rosen experiment. EPR is a thought experiment, and that dates all the way to, 1935, and that was answered a few months later by Niels Bohr, who was on the other side of the issue, trying to defend quantum mechanics against the attack of EPR. Okay, and what was EPR? Well, EPR is essentially entanglement. You could say the same thing. Okay, they just changed their names, the name of the experiment, or the thought experiment, over the years, and supposedly they proved it later on. Okay, what's the issue? Here it is. Okay, in a nutshell, here's entanglement for you. Okay, if you are afraid of words, say, oh, what do they mean by entanglement? Don't worry, it's kid stuff, baby stuff. Okay, a little 10-year-old can understand this. Okay, here it is. Okay, we have entanglement, and the question is, why do two photons, right, emitted from the same atom, spin in opposite directions, although miles apart? Okay, so that's the whole issue. Here you have an atom, it shoots a photon in opposite directions. Okay, and if you measure one of the photons going clockwise, the other one will go counterclockwise, and vice versa. And if you were to be able to reverse the direction of that particle, of one of the particles, the other one instantly, and that's the key word, instantaneously, right? Changes direction as well. Okay, so that's the whole issue. And the question is, how do you do this with particles? Okay, there you see the particles on the bottom. These particles, especially in the case of light, they're talking about photons. And what are we saying? We're saying that all these photons in a series, right? They're going through a certain detector on one end. And what's happening is they're measuring, and they say, well, these are pointed in a certain direction. Okay, and the ones on the other side, they're pointed in a different direction. And they were able to measure this at great distances. And they said, we don't understand how one photon, right, on one of the analyzers is able to influence one on the other side of the universe, really, instantaneously. How can it possibly do that? Okay, so that was the whole issue. And Niels Bohr and Einstein, they debated this issue personally, and also through articles that they wrote, that they authored. Okay, and this is more or less a summary of how each side thought, or what each side proposed. Okay, here you have it. The elements of physical reality which are objectively possessed cannot be influenced instantaneously at a distance. That was the whole issue from Einstein's point of view, the word instantaneous. They could not make sense of it. They could not make mathematical sense of that. Okay, that was the issue. Okay, so what was Niels Bohr's answer? It was their arguments, referring to EPR, right? Einstein, Podolsky, and Rosen. Their arguments do not justify their conclusion that the quantum description, okay, turns out to be essentially incomplete. So both sides were essentially arguing whether it was feasible at this point. And in the case of Bohr, he was just talking about a description, whereas Einstein was talking about an explanation. He was saying, how do you influence something instantaneously when he had already proven, supposedly mathematically, right, through special relativity, that the speed of light is the maximum speed of the universe, and it travels at 300,000 kilometers per second. So if that was the finite speed, or the maximum speed limit, what was this instantaneous stuff that they were bringing in with EPR and with entanglement, what became known as eventually as entanglement? And Niels Bohr never came up with a mechanism. He just said there are no hidden variables there, okay, locally to make this happen. He just said it happens. It is so. That's all he said, essentially. And what came later on here were the experiments of these fellows, Aspect and a couple others. And they said experiments verified entanglement. They verified entanglement. In other words, they confirmed that entanglement occurs. Okay? Aspects of experiment imply that a hypothetical coordination signal travels twice as fast as c, c being the velocity of light. And another fellow there reached 10 million times c in his experiment. So he says, essentially, it was instantaneous. So what these people were doing is measuring and to confirm that the description was correct. In other words, the one proposed by quantum mechanics / Niels Bohr, that it was correct, that it did indeed happen in real life. That was not just a thought experiment as Einstein, Podolsky, and Rosen proposed. It actually happened. And they never explained it. They never gave you a mechanism. Even to this day, there is no mechanism. They gave these people a Nobel for essentially running an experiment, confirming the description that, yeah, it travels, you could say, instantaneously with 10 million times the speed of light, and that's about as instantaneous as it gets, and that's the best they could measure. And so this is what they do. They measure and they say, oh, the description is correct. But they never explain how Mother Nature does the trick. So we still don't have an answer from the mathematical establishment, okay, on entanglement to this day. Okay, so you can look at anywhere and they say it's true. It happens. Okay, so it's true, it happens. How does it happen? Especially if you're sending particles one way or waves. You want waves? We'll do waves, no problem. You send them one way, okay? It has to travel. Does it travel instantaneously? Is that what you're saying? Okay, because we're talking, again, one-way flow of whatever. And how do we do it under the rope model? Well, kid stuff, baby stuff, okay? So you do not need to take any math. You do not need to go to college. If you're a 8-year-old, 9-year-old, 10-year-old kid, I think you're going to understand this quite well. Okay, here it is. Okay, do we have to explain anything? Absolutely not. But I'll explain something in the background. Here you will see the images of what entanglement is. Okay, how Mother Nature does this magic trick. Okay, and here it is. Once you connect every atom in the universe with a rope-like entity, then a rope being the carrier, you could say, of light. In other words, the rope, torsion on the rope, local torsion on the rope, is already light. And so you do not have anything moving really from A to B. What you have is simply a rope that is torquing from the other side of the universe all the way to this side of the universe. So an atom on the other side of the universe that is connected to an atom on this side of the universe have a rope torquing in a certain direction, okay? And if you're on one end of that, you would see that it's clockwise. If you're on the other end, you had better see counterclockwise. That's essentially the whole thing. And here, I'll show you something else here. Give me a second here. For those of you who are not familiar, we're looking at the construction of the atom and the rope, okay? And here it is, okay? That's what our atom looks like. You see the ropes impinging on the surface of the atom. Okay, and here you see the construction. Okay, one thread, which we'll arbitrarily call the electric thread, goes through the center of the atom, and many of those from every atom in the universe form a proton star. The magnetic thread coils around, forms the electron shell that encapsulates the proton star, and you can see how all those ropes are connected to every atom in the universe, and that's what the atom looks like. So what you have here is that the atom itself is connected to the rope, is connected to another rope on the other side, but these ropes form the atom itself. It's a continuous entity. In other words, the thread just moves throughout the whole universe. There's a single thread in the entire universe. So we can see why if the atom torques, right? If the atom torques, then what you will have is that from one atom's point of view, it's going to be clockwise. And from the other point of view, it's going to be counterclockwise. If somehow you were able to reverse the direction of that rope, right? Again, I usually have it with my rope here. You know, from my end, let's see, there we go. From my end, it's going counterclockwise. Hopefully from your end, if I can do this better. Yeah, from my end, it's going counterclockwise. From your end, it should be going clockwise. And now if I reverse it, from my end, it's going clockwise, and from your end, it had better go counterclockwise. Very simple stuff, okay? With a rope, it's baby stuff, kid stuff. With particles, oh man, you'll never get it with particles.